Right, so now I'm going to start the next video. Sorry, just a bit of uncertainty there because of the some technical issues. This is the next video on the topic of further mechanics. I haven't done any videos on this for quite a long while, but basically I already did 3 videos on simple harmonic motion, excuse me, which I think is one of the hardest topics. This one is also pretty hard. It's called Equilibrium of Rigid Bodies, which is a bit of a long, strange title, but I suppose the key word is equilibrium, meaning a situation in which there is no resultant acceleration and no resultant rotation, or rather no resultant angular acceleration. So it's one of those things that's an easy enough idea in simple terms, but getting the definitions exactly right can be tricky. And that's reflected in the topic as a whole, in that the ideas seem simple on the surface, but they can be difficult to carry out in practice. Now on the screen you see just the section of the syllabus that's particularly related to this topic, equilibrium of rigid bodies. I mean, I can just briefly read through it, but it's not probably necessary to do that. The first section talks about gravity and asks you to pay attention to the position of the weight force. The second section talks about moments, which I'll talk about again in a minute. The third section here, recall that if rigid body is in equilibrium, then the vector sum of the force is 0, the sum of the moments of the forces is 0, which is really just an elaboration of the concept of equilibrium. The fourth bullet point here, use Newton's third law, is actually something that trips people up very often, although strictly speaking that is not new knowledge. That knowledge you should already have from studying M1, but students often find it more difficult than it probably seems. The last bullet point doesn't really say anything, I don't think. So I'll leave the syllabus there. Obviously you can read it. There is maybe some other things to mention, but I thought I would make notes here in regard to what are really the important things. So first of all, friction. Maybe I'll just write in red here. Friction, we have to recall what we learned in M1, which is that the frictional force is less than or equal to the coefficient of friction multiplied by the magnitude of the normal contact force. The direction, it's difficult to state exactly, but if we're talking about equilibrium, then we're talking about objects which are not accelerating. And actually, I've suddenly realised I don't think any of the exam questions that you'll see in this topic involve objects moving. Although strictly speaking they could. If they were moving with constant speed, we could still have equilibrium. But generally speaking, we're going to be focusing on cases of statics, objects not moving at all. And in those cases the direction of the friction is sometimes a bit difficult to identify, because the basic rule of the friction when objects are not moving is that the direction is, how to put this clearly, opposite to the direction in which relative motion would occur between two surfaces if friction were not present. So I know that's a horrible sentence, but I'm basically talking about the case where there are two objects in contact on a surface. So here perhaps are 2 boxes, upper box and lower box. And in order to decide whether the friction force points one way or another on each object, we should consider what would happen if friction were not present. Thus, for example, if I push the lower box, if there were no friction, then the lower box would move forwards relative to the upper box, which means the friction acting on the lower box in this surface here would be that way, to the opposing the original force. If it's called P, it would be in the opposite direction to P. Because let me repeat, because if there were no friction, then the lower box would move to the left relative to the upper box. Imagine it like an icy surface, then the top box would not move forwards with the lower box. So that would create a tendency for the lower box to move to the left relative to the upper box, so the friction force acting on the lower box would be opposite to P. The friction force on the upper box would be in the opposite direction to the friction force on the lower box, and you deduce that from Newton's third law. Sorry, I'm having a bit of a problem with a dry throat here. Just give me a minute to pause. Okay, pause finished. So think about the direction of the friction force. It is an issue. People often do get it wrong. So let me just remove that. Direction opposes motion. Opposes potential motion would be good enough in most cases to understand it. Let me write that down. Opposes motion. Potential motion. Normal contact force, also important and often not well understood, is the direction of the normal contact force. The exact definition of this. Direction. Okay, the magnitude is whatever is required to prevent, let's say, violation of the surface. Sorry, that's a difficult word. To prevent falling through a surface. The direction is perpendicular to the surface of contact. Now, people often gloss over this. They don't think too carefully about it, but you need to think carefully about it. Think about different cases. Here's one case. A triangle on top of a box. No problem, right? Because the surface of contact, I'll mark it in a green colour here. It's there, isn't it? Obviously, that's the surface of contact. Obviously, the direction perpendicular to that is upwards on that diagram, on that rather messy diagram. So that's easy. But there are cases which are not easy. What cases are not easy? If we have, what would be a good example here? Right, if we have a ramp or slope, and then we have maybe a rod touching the slope. So think of this as a ramp, a non-horizontal surface, and then a rod there. Well, what would be the direction of the normal contact force here? Because there is a contact force if the rod is touching the ramp, yeah? Well, the answer is perpendicular to the surface of contact means perpendicular to the ramp. It can't be perpendicular to the rod in any sense because the rod is considered to be a one-dimensional object. It's just a line. So there's only a point of contact here, not really a surface. But you can treat the ramp itself, because the ramp is a surface, as the surface of contact. Yeah. So that's how you would answer that case. Then there might be more difficult cases. For example, let's just erase this diagram. There might be more difficult cases like two curved surfaces touching each other. Let's try that. This is not going to be very well drawn, but here's a surface and another surface touching each other. Maybe it's like two solid balls touching each other. Well, I hope you can see immediately that there's no problem here, because in order for the two surfaces to touch at one point, they need to have a common normal, don't they? At that point where they touch, oops, that's supposed to be a line. The normal line is common to the two surfaces, so inevitably that will be the direction of the normal contact force. Don't forget, of course, like all forces, normal contact forces come in Newton's third law pairs, so there's always two of them between the two objects that are touching. Now, what others? There is one more case which I hope you will find confusing, which is, what if I have two rods touching each other at a point? This case doesn't really work in itself. first of all, no object is really one-dimensional, right? So really a rod does have more than one dimension. So if you imagine these as two rulers, yeah, of course they have a real surface at the top where they would touch. But in a more likely case that you'll come across is if there's a kind of circle here on the diagram, and that would reflect something called a hinge, or even sometimes might be called a pivot, but it's more really a hinge, which is where you create a kind of contact such that the two rods can rotate while keeping this point fixed. The best example would be a door. A door has a hinge. There's a door opening out onto a room, let's say, and here it will have hinges which allow the door to rotate. So imagine a hinge. Well, clearly in this case we can't really apply the rule perpendicular to surface of contact. So we consider that in the case of hinges there's a kind of special rule, which is the normal contact force can be in any direction whatsoever. And what you have to do is use the other conditions within the question to decide, in the case of a hinge, what is the direction of the normal contact force. So the way to remember it is this. The general rule is the normal contact always points perpendicular to the surface of contact if there is a surface of contact. If there is not, because the contact is some form of hinge, then you consider that as the normal contact can point in any direction. And I've just realised I've forgotten a very, very important point in saying all this. I've forgotten that this is all for free contact. In other words, none of this rule, I'll put it in brackets, this rule only applies for free contact. For example, consider this case. Suppose we have a beam, a wooden beam, sticking out of a wall, and somehow the beam is attached to the wall. So key word here would be attached. If it's attached to the wall using glue, using nails, using any kind of, like I've illustrated here, maybe it's stuck inside the wall, then this is not a free contact, and in this case the direction again can be any direction at all. And again, you have to use the other conditions in the question to help you decide what the correct direction is. To give an example of that, suppose we had two ladders joined with a hinge at the top, and we wanted to find the normal contact force between. Sorry, I should stop saying normal contact force. If the contact is not free, then the word normal doesn't really apply, because as we've just said, this rule perpendicular to surface of contact doesn't really apply in this case. So if we have a hinge, we have a contact force between the two ladders, but its direction is unknown. And the best way to deal with that mathematically, let's call this R, the contact force, is to split the contact force into two perpendicular components, like Rx and Ry. And that might help you if you use a method of resolving to find the vertical net force and the horizontal net force. Then you can find Ry and Rx. But note, of course, it means that there are two unknowns there and not just one. Alright, I've said enough about normal contact force. I now need to talk about moments. I won't talk about Lami's theorem today. I might talk about it in the next video. I'll find an example where that's important. So moments, there is something important to say here too. So I think I'll just draw an arrow and give my next little speech here. So what do I want to say about moments? By now you almost certainly have learned at some point in school how to take moments in simple one-dimensional situations. For example, if I draw this kind of diagram, that should be a straight line. No, I'll try that again because it's too annoying otherwise. Excuse me while I just spend a moment doing this. Okay, so here's a line, not a very good line, never mind. And you've almost certainly seen problems like this: a 3 Newton weight, perhaps 10 meters of distance here, perhaps 15 meters of distance here, and a 2 Newton weight here. Now this point I've drawn with a triangle is usually called the pivot. It can also be called a fulcrum, but that's an unusual older word, I think. So we'll stick with pivot. Now you've almost certainly learned to evaluate this kind of situation by saying, well, 3 times 10 is equal to 2 times 15, and so this is in equilibrium, or is in specifically rotational equilibrium, because it does not rotate because what? Because two things are equal. The left-hand side of that equation is the anti-clockwise moment, and the right-hand side would therefore be the clockwise moment. If you think about clockwise and anti-clockwise rotation, then it's pretty obvious what's going on. And that's clockwise moment, that's anti-clockwise. Now I'm not going to waste any more time on that, but bear that idea in mind as I say the next thing, because what I want to show you, which you may or may not know yet, is that the position of the pivot is not... there's two different concepts here. There's the pivot physically. Here, this system remains in equilibrium for only one reason, which is that we placed the pivot here. If we remove this pivot, then of course the system would do what? If I remove this pivot, what would happen to the system? Well, of course it would fall downwards, wouldn't it? Because there are two forces pulling this beam. Let's say it's a wooden beam. There's 5 newtons of force pulling the beam downwards, so that it certainly would not stay in equilibrium, right? So to get both linear and rotational, excuse my handwriting, equilibrium, we need, two different things to be true, don't we? We need first that this equation adds up, that 3 times 10 is equal to 2 times 15, so that it doesn't have more pulling it to turn clockwise than anti-clockwise, but also that the forces balance up, down, and to the left and to the right, yeah? So this system of forces acting on the beam, let me replace this sort of physical diagram with a purely force diagram. And let's use that. Maybe we should use a different colour for the forces. So what I'm going to draw now is a free body diagram. And a free body diagram is a diagram in which you draw only one object. So that's the 3 Newton, that's the 2 Newton, and this of course is a 5 Newton force. So the red arrows show all the forces acting on the wooden beam, but also note that that diagram does not show any other forces, it only shows the forces acting on the beam. So that's why we call it a free body diagram. The word free here just means that you can't see anything else. The body concerned, which is this beam. Maybe I should write the word beam so you know what I'm talking about. Beam. This wooden beam is free in this diagram in the sense that it is not connected to anything else. In the real world there is another body connected to it. There's a pivot sitting here. But in our diagram it's on its own, so that's why we call this a free body diagram. At first, when you're shown this idea of the free body diagram, you probably think it's not very important. It's just a way of drawing a diagram, but actually it's very, very useful. Don't underestimate it. So as we start to look at difficult problems, consider ways in which you can draw free body diagrams of the various items. Now I'm trying to get on to the main point about moments here. We said that physically there was a pivot in the centre here. Well, not the centre, but in that point. Let's call that point O, like origin. Well, there's two ways in which we use the point O. We considered it physically as the point where we place this 5 Newton force. but it was also the place that we used as the center for this equation, wasn't it? Think about that. We looked at this point here and we measured the distance of the 3 Newton force to that point, 3 times 10, and we measured the distance of the 2 Newton force to that point. But what's to stop us from using a different point? Let's say, oops, sorry, this is not going to work easily. Let's use a point P here and recalculate the net moment, the clockwise moment and the anti-clockwise moment about P instead of O. And here we have a very useful common notation, which is that we write a letter representing the point which we're using as the pivot for our calculation. So we used O as the pivot for our calculation. Now let's use P as the pivot for our calculation. What happens here? Well, we still get the 3 Newton force, but now it's distance. Oh, sorry, what is P's position? P is a distance of 10 meters from O. So we get 3 times 10 plus 10, so that's 3 times 20. And that is a anti-clockwise moment. Now we notice that both the 5 Newton force and the 2 Newton force act clockwise around P, don't they? So they both appear on the other side of the equation, and we get the 5 Newton force multiplied by a 10 meter distance plus the 2 Newton force multiplied by a 5 Newton distance. And we see that this equation is absolutely correct, that it shows that the anti-clockwise moment is also equal to the clockwise moment for the pivot point P as well as for the pivot point O, understanding clearly that the physical pivot is still at O because the contact force of 5 newtons is pushing up there. Now, this is all very basic, but I think if I don't show you this first, you definitely won't understand the next bit. That's why I'm doing it. So it's clear that choosing any pivot point along the beam, whether it be here or here or here or here, anywhere along this beam, we're going to get the same result, which is that the clockwise and anti-clockwise moments balance. And physically that's excuse me, that's obvious, because if any one point on the beam is going to rotate, then all of it will rotate. So if it's in rotational equilibrium at O, it must be in rotational equilibrium generally. Now it's a little more complicated than that, as you'll see in a minute, but that's the basic idea. So what's the next step thinking about moments? What I want to show you is a kind of a theorem that let me state it in words first. If we have linear equilibrium, what does that mean? It means the sum of all the forces is 0, and sum of moments equals 0 about one pivot. Then, so if then, yeah, let me just maybe mark that clearly. If then sum of moments equals 0 about any pivot. Oops, about any pivot. And now let me prove that statement mathematically. What does it say? It says that linear equilibrium means that the sum of all the forces acting on an object, so imagine summing over some index I don't really care how many forces there are, I'm just going to add them all up as vectors and get a 0 result as a vector. So if I know that to be true, and I know this, let's draw a diagram. Imagine some irregular body. It doesn't really matter what the shape is. Imagine some point which we can consider as our origin. And we have to imagine a bunch of forces. It doesn't matter how many there are, F1, F2, F3, ... F54, I don't care. Now notice forces act along particular lines, and therefore they are at particular distances from the origin, which is what allows us to measure their moment about the origin. If I wanted to measure the moment of F1, I would have to multiply F1, the magnitude of F1, by the distance x, which is a perpendicular distance of the line of action of F to x to O. So, going back to our theorem, if we have linear equilibrium and we have that the sum of the moments, now bear with me, I'll explain this in a minute. The sum of the moments Fi cross Ri equals 0. So what do I mean there? Well, cross here is the cross product, and the definition of the magnitude of the cross product is let's say Fi cross Ri would be written as the magnitude of Fi, so the newtons of force, times the distance, times the length of the position vector of the point at which Fi acts, which actually is ambiguous, but okay, times the sine of the angle between those two vectors. So what we're saying here is that if we've got a force and a position O, to get the perpendicular distance, we need the angle. So suppose the point is up here somewhere, so that this is Ri. Then the angle between them is theta, so that's theta. So the distance we're looking for to make the moment is Fi times d. Sorry, Fi times d, and d is Ri times sine theta, as you can see from this right-angled triangle. Sorry for that messy diagram, but it's something you can check for yourself later if necessary. So you see that what we're writing here is that if we choose a particular point, and I'm calling that point the origin to make the calculation simpler, and we know that the sum of the moments about O is 0, then we also know that the sum of the moments about every other point, both inside and outside the body. So in other words, I could choose a pivot down here if I wanted to, outside the body, or any other pivot inside. I'm going to find that the sum of the moments about that point is also 0. Now, why is that mathematically? Mathematically, it's because if I choose an arbitrary other point, I'll choose it outside the body just for simplicity, call that point P, and then we'll call the position vector of P itself as R0 or RP. There we go. So that will be a fixed vector. Yeah. Now let's write the sum of the moments of all the forces Fi about the position P. Well, here we have to shift the position of the origin, don't we? We have to say the vector. We have to write the vector from any particular force or point on the line of action of any particular force to P. Well, it's clearly RP minus RI, isn't it? Now, is this equal to 0? Well, let's use first the distributivity rule, so we can distribute this over these two vectors. If you don't know that the cross product is distributive, it doesn't matter. You can just believe me and check it later. It's kind of obvious. We've got Fi cross RP minus Fi cross Ri. Okay, so now what's that equal to? Let's look at these two terms. The second term is the easy one because we've already written, let me underline it for you, that the sum of the moments about the origin, which is these Ri's here, must be 0, so this is equal to 0. Now, why is this equal to 0? Well, I suppose it's most obvious if we rewrite in terms of the definition. We have the magnitude of the forces Fi times the magnitude of Rp times the sine of the angle between them. I've just had a bit of a change of heart about this. I think maybe an easier way to understand why this first term is 0 is not using the definition of the cross product, but rather just again using distributivity. In other words, we're going to use the fact that A cross B plus C equals A cross B plus A cross C. So that of course could be written as, let's say, F1 cross RP plus F2 cross RP plus ... up to the maximum, the final one, yeah? All of these are vectors, of course, so underline them. And this we've decided is already a 0. Well, we can rewrite that again using distributivity, just using the fact that it distributes. Oops. That should be plus up to the last one, whatever it happens to be. And of course that's 0 cross RP, and that indeed is 0. The 0 vector. So we've shown from that proof that is it a remarkable fact? It's very obvious in one dimension, but I think in multiple dimensions it's less obvious that if we know the body is has a 0, if we know that the system of forces acting on the body has 0 moment about any one pivot, then it will have 0 moment about any other pivot, whether inside or outside the body. And if all this seems too technical and a bit abstract, well, fair enough, but the reason I present it is because this fact is probably the most important knowledge you need to solve the problems that you will be presented with in the exam. Okay, so now we're going to go on and start. Oh, sorry, just to be clear, so we've discussed, let me do a little tick list here. We've discussed friction briefly. We discussed some details about the normal contact force. It's actually a bit more complicated than you might think, isn't it? And also the main principle that we're going to use with moments, which is that we equate, or rather we find the sum of all the moments to be 0, treating anti-clockwise as positive and clockwise as negative, or vice versa. But also we use this crucial principle that we can choose the pivot point wherever we want if we know the system is in linear and rotational equilibrium. And also now just to clarify again that what we're basically saying in this topic is that bodies are rigid, meaning that all parts of the body move with the same speed, same angular speed, they rotate together, they accelerate together, or whatever. And under those conditions we consider a body to be in equilibrium if it is not moving in any direction and not rotating. And we use that principle to solve the problems. Okay, enough. So that's some basic theory. As I said before, the basic theory seems quite limited and simple, but doing the problems is much harder. Let me show you one problem in this video, and then in the next video we'll go on to some problems of slightly different types. Here we go. Right. So here's the first problem I'd like to consider. This is from Winter 2010 CIE paper. I'll just briefly read it. A hemispherical bowl of radius r is fixed with its rim horizontal. A thin uniform rod rests in equilibrium on the rim of the bowl, with one end resting on the inner surface of the bowl at A, as shown in the diagram. The rod has length 2a and weight w. The point of contact between the rod and the rim is B, and the rim has centre C. By the way, the rim here is the top of. You can think of this, if you like, as like a bowl of noodles, and this is like the chopstick, just a single chopstick. And when they talk about the rim, they're talking about the top level of the bowl. So where was I? The point of contact between the rod and the rim is B, and the rim has centre C. The rod is in a vertical plane containing C. So this sentence often appears in questions just meaning that you don't need to consider the third dimension. You can consider that everything is in one plane. The rod is inclined at angle theta to the horizontal, and AC is inclined at 2 theta to the horizontal. The contacts, AC? Yeah, the rod is at theta to the horizontal. That's right, yeah. The contacts at A and B are smooth. That's important, so we can ignore friction in this problem. In any order, show that, and then it gives you 3 equations to show. Okay, so first of all, in any order is quite significant because it's telling you that there is more than one way to approach this question. It is more common that they will guide you and tell you something simple to find first and then allow you to build up from there. Here they're letting you start in any place you want. But at least let's make a list of what we need to know. We need to know the contact force at A, the contact force at B, and also this equation about theta. So let me go to my notes, and now we'll look at the diagram here and we'll try to annotate it. I haven't looked at this question for a while, so I may forget some basic facts. So first of all, it said that, well, we can see from the diagram that the angle between the horizontal and the rod is theta, obviously, because that's theta and that's 2 theta. Oh, and that's theta as well, of course. Obviously these are theta because these are the radius. Now, is the radius r? Yeah, the radius is r. So that's r, that's r. And also we know that the length of the rod is 2a and its weight is w. So at some point there will be the middle of the rod. The weight will be w, and then we'll have an a here and another a here. So that's just some basic geometry and lengths, but we're asked to find the contact forces at A and B. So if you carefully followed what I explained at the beginning of the video, you will know the directions of the contact forces at A and B. If you don't know, think about it, pause the video, and then come back and I'll tell you. So the direction of the contact force at A will be perpendicular to the surface of contact, which here is the surface of the bowl. So the direction perpendicular to the surface of the bowl is the direction along the normal line, which is along the radius. So I'll call that NA. That's the normal contact force A, or the contact force A. There is no friction force, so the contact force is the normal contact force. Please listen to my sentences carefully. If you don't quite follow, you might need to listen very carefully. What is the direction of the contact force at B, though? Well, here we have the opposite case, because here the rod itself is the surface. The bowl is hitting the surface of the rod, you see. So therefore the direction of the normal contact force at B must be perpendicular to the surface of the rod, not of the bowl. And the majority of people who get this question wrong get it wrong because they fail to draw those two arrows correctly. And now we should consider the question, what is the easiest way to find NA and NB? Now we've just learned, or tried to prove anyway, this very useful fact that we can take a pivot anywhere. We know that the system is in both linear and rotational equilibrium. Therefore, we could resolve forces vertically, we could resolve forces horizontally, or we could take moments about any pivot that we choose. Let's look, for example, at those first two equations again. The contact force acting on the rod at A, the contact force acting on the rod at B, in terms of W and theta. Okay. Well, here's what I'm seeing. If I want to find, let's use black. If I want to find NA as a function of W and theta, then it means I don't want NB to be included in the calculation. So it seems there's a couple of ways to do that. The most obvious way, I think, is to take moments about which point. Can you tell me which point I should take moments about? Yeah, that's right, B. If I take moments about B, then hold on a minute, maybe that's not the best way. Excuse me, I am doing this in real time, so occasionally I will say things that are a bit wrong. If I take moments about B, then I need to know the perpendicular distance of W from B. Oh, it's not so difficult, is it? Yeah, because we can easily measure the distance AB. Let's do some basic geometry first. What's the distance AB? Well, that distance is the bottom of this isosceles triangle, so it's twice r cosine theta. Maybe I could just drop a little perpendicular here to make that obvious. R cosine theta plus r cosine theta equals AB. If I call this point, I should give it a name, call it D. Therefore it follows that BD equals AB minus AD equals 2r cos theta minus A. A is the distance from the weight force to the end. Sorry, I couldn't find a way to draw that neatly. So I've got BD. Okay, this might not be the best way, but it will certainly work. If I now take moments about B, I'm going to get the following equation. Sorry, always be clear. I'm taking moments about B, but for which object? For the rod. And I'm getting the following two moments. W times what distance? BD cosine theta. That would be the anti-clockwise moment. The clockwise moment is caused by NA. Now to find that distance, that perpendicular distance from the line of NA, the line of action of NA, which goes up here, to the pivot point B, I need to look at that triangle, and I can clearly see that what I need is AB times sine of theta times the force NA. Now these distances BD and AB I already know, so I can rearrange this equation. NA equals W 2r cos theta minus A, that's BD, times cos theta divided by, whoops, that's horrible, isn't it? Let me try and do that again. All divided by AB, that's 2r cos theta, times sine theta. What am I doing? Oh yeah, AB sine theta. That's it, right. Okay, so need to tidy this up a bit. What is the final form that we're looking for? W tan theta. Wow, really? Excuse me. There might be something slightly wrong with that. I'm not sure. Oh, the cos theta cancels, but NA times. Perhaps I've missed the force. No, I don't think so. Okay, so this is not exactly what we want, because we want this to say W tan theta. But this, to some extent, is the big problem with these kind of questions, is that you can go in so many directions with the algebra because you can choose different pivot points. So what I think I'll do is I'll just stop there. Even though that's not the form I want, it doesn't mean I'm wrong. What I should do, therefore, is see if I can generate other equations which give me other relationships between these variables r, a, and theta. So what I didn't really appreciate is that the variables r and a both appear in that equation. so it might have been wiser to choose a slightly different approach. But it's not a reason to panic. Yeah, you just simply look at some other alternatives. For example, in a way you're spoiled for choice. You can look at horizontal and vertical resolving. You can look at resolving along the rod and perpendicular to the rod. And you can also look at choosing other pivot points. It's certainly possible to choose A as a pivot point, get another equation, or choose C as a pivot point. See, notice C is not inside these solid objects, it's outside them, but it might be a good pivot point to choose because you notice that NA, the line of action of NA, passes through C, therefore there would be no net moment from NA. You would only get 2 moments. But I think for consistency, given all these choices, they're very reasonable choices, I think, so that I'm not wasting my earlier work, I think I will next write down the equation of rotational equilibrium about the pivot point A. See what I get there. So if I write, what am I doing now? A. Moments about A for the rod, I get what? Well, NB is an easy one. NB is perpendicular to the rod, so it's simply NB times AB. Times the distance AB would be the anti-clockwise moment. The clockwise moment would be W times the distance A cosine theta. Now AB we already discovered was 2r cos theta, so I have WA cos theta over 2r cos theta. I believe that's right. So it's WA over 2r. Is that right? Yeah. So NB, cos theta cancels, I'm getting W, did I get that right? Cos theta, yeah. WA over 2R. And again, this is not the form that's given in the question, but no reason to panic, I think. Yeah. Yes, actually, it's obvious that that answer corresponds to part 3. So what we need to do now in part 3 is find a relationship between without W between the variables r, theta and A. So I want to find now a relationship between r, theta and A which will allow me to substitute into these 2 equations. Let's give them names or something. Call this oops. Can I undo that? Quite sure what happened there. Can I substitute into these equations? Yeah. Okay. So how do I get a relationship between r, theta and A? Well, what I notice is that between r, theta and A means that I'm not including W at all. Can I get this geometrically, or can I get it from eliminating W from the equation? Perhaps I can get it from eliminating W from the equation because I can resolve horizontally. Yeah, I think so. So if we look at the forces acting horizontally on the rod, there are only 2. All I need to know is to make sure that I know this angle here. So if this is theta, let's be careful here. That's theta, that's 90 minus theta. Oh, I see. So that's 90. The angle between NB and the rod is 90. So that's 90 minus theta, isn't it? Let me just draw that in blue. So that will make life easy, won't it? So if I resolve horizontally, then naturally the W is not included. So sometimes we write this, and we get NA times, I think it's cos, NA times cos 2 theta actually, isn't it? Yeah. Equals NB cos 90 minus theta, so that's NB sine theta. Sorry if you couldn't exactly see that. I'm sure you can go back and review the diagram there. It's just, yeah. So that's our third equation. That should be all we need. All we need to do now is to tidy up. For example, I can substitute for NA and NB using 1 and 2. It'll look a little bit complicated at first, but I think it will cancel out. W, this is a long thing, isn't it? Let's save ourselves some writing time here. Whoops. Copy that. Yeah. So that's NA times cos 2 theta. Oops. Equals NB, which is WA over 2R times sine theta. So we see that W cancels, of course, and hopefully there'll be some other cancellations too. Let's have a look. The cos theta, of course, cancels there. And what else? The 2R cancels, that's useful. So what is left? 2R cos theta minus A times cos 2 theta equals, I think, sine squared theta. That doesn't look exactly correct to me. 2R cos 2 theta equals A cos theta. Did I miss something here? Horizontal forces. Sorry, just forgot to multiply by A there. Certainly this kind of cancellation is a bit dangerous. Try to write as neatly as possible. I can't really do that here. So you get A sine squared theta, which makes a bit more sense, because now if you put all the terms with A on the right hand side, you get 2R cos theta cos 2 theta equals A cos 2 theta plus sine squared theta. And if you remember, cos 2 theta is cos squared theta minus sine squared theta. We get A cos squared theta, which 1 cos theta cancels, so we get 2R cos 2 theta equals A cos theta. So that is part 3. And then we can substitute, what do we need for NB? NB, the normal contact force at B, was W cos 2 theta over cos theta. Just substitute A over R. So therefore A over R equals 2 cos 2 theta over cos theta. Therefore NB equals W over 2 A over R equals W over 2 cos 2 theta over cos theta. So that's part 2. You can write QED if you like, just to make it clear that you've finished. And then part 1, excuse this was just some random drawings here. Oops. That's quite fun, isn't it? Nearly finished. The last step. Substitute, so NA NA equals the original formula, cancelling the cos thetas, was W 2R cos theta minus A over goodness, 2r, let me get this right, 2r cos theta minus a over 2r sine theta, that's right. And then we can just replace this saying a equals, so w 2r cos theta minus a being 2r cos 2 theta over cos theta and all of that is divided by 2r sine theta, so we can cancel 2r, 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 and we can also multiply by cos theta everywhere, so we get w cos squared theta minus, let's get this right, cos 2 theta, and that's divided by sine theta cos theta, I think, equals w. So again, cos 2 theta is cos squared minus sine squared, so I've got w sine squared theta over sine theta cos theta equals w tan theta QED. That's the first part. Alright, so I made that one a little bit longer than I probably needed to, but it all depended on how you started. You really do have a choice how you start this problem. It's very much worth carefully considering what variables you want to appear in the equation. I think I may have made a slightly bad choice. If we wanted to prove this theory first, that NA is W tan theta, we would need to somehow make sure that the distances we were measuring were all related to the radius r or related to the distance a, and not a mixture of both, which is what I did. So looking again, if I wanted to get NA equals W tan theta immediately, I should probably resolve perpendicular to the rod. If you resolve perpendicular to the rod, imagine this direction here, well, we get NA times the cosine of theta going upwards. Let me write it here. NA cosine theta, that's upwards. Of course, this is not going to be enough on its own, because then you would also get NB, and that would be equal to W times, I think it's the cosine of theta. Yeah. And then if you resolved parallel to the rod, along the line of the rod, you would get NA, oh sorry, that's sine, isn't it? That there is sine. NA sine theta. And then if you resolved parallel to the rod, you would get NA cos theta equals W, there it is. Resolving parallel to the rod gives you NA cos theta equals W sine theta, which immediately gives you the first result. So that's much, much quicker. So I hope the fact that I hadn't prepared that carefully in advance didn't spoil it too much for you, but I think it's much more realistic to show you how it works in practice, which is that if you're not extremely careful and thoughtful about which of the various equations you choose to write, you can end up, like I did there, wasting a good 10 minutes on extra algebra that isn't really necessary. And most students aren't really that confident of what they're doing, and so if they end up with an expression like this, this one here, a lot of students lack confidence and they'll just assume that they've made a mistake and they'll get very worried. Actually, that was totally right. I didn't make any mistake there. It's just that it's not what the question was asking for. And I had to go around a rather long, complicated method to get to the final result. So, it's up to you to deduce from this kind of presentation what it gives you, how it helps you to understand. But I hope in the next video I will show you probably 2 more exam questions of similar but also slightly different types. And I hope to give you more insights into how to make these problems as easy as possible. I mean, that right there that I showed at the end is another good example of how much easier it can be if you do it right. So see you next time.